Okay, so this is a new section. This is the last section in topic 30, I don't know, 30, right? So we start talking about the design issues. So this is LCC inverter example, and this is a bad choice for the MOSFET switch because this LCC structure has some problem. So we'll see that. Okay. Spec for this design is shown here. Design specification structure is LCC inverter, but this is the same as the LCC converter. Okay, only difference is this output stage, rectifier and filter, but we have the number, conversion number, then the inverter becomes converter. Okay, so same thing basically. And design spec, input voltage 160, and the switching frequency is 100 kilohertz. And this output voltage, this is RMS, this is peak value. So peak value is this number, and output power is 25 watt, right? So this is the output power, is product of IRMS and VRMS. So this number is given here. So by multiplying square root 2, you have the peak value of this. Then by dividing this, it really doesn't matter whether you use RMS value or peak value, is the same number, and R is 900 ohm. Okay, so this is specified from the input voltage and output current, output voltage, output power, all right? But we need one additional information here, at least one additional information to design the tank circuit. So another specification is this one. The open circuit, our voltage, magnitude of that is this one. Okay, this is magnitude. I should use OC. I don't know why I'm using OS. There is a mistake. Should be open circuit, short circuit, like that. So this is the design specification. From this, first you need to specify the ellipse, inverter ellipses, and you need to specify two parameters for the Thevenin's equivalent circuit of this tank. Then the design is almost finalized. Okay, so for that, this additional information is necessary. But if this is not specified by some reason, then you assume this some reasonable value, then start designing the tank circuit. Okay, so first one is inverter ellipse at this switching frequency. This switching frequency is given in advance, and ellipse equation is this. All right, so there are 4 variables, but 3 variables are already known. We know this. This is given by the spec, and this is given by spec, and this is derived from the output power requirement. So 3 values are known. The remaining value is determined like this. So we have 4 variables, all known. Then we have the ellipse equation. This is ellipse equation. This VOC, open circuit voltage, is 400, and ISC, short circuit, is this one, 0.278 M. Okay. So this is the ellipse equation. And next step, this is Thevenin's equivalent representation of the tank circuit. So we should know this, GOO. This is output impedance evaluate with this circuit, show it. And this is the voltage gain, open circuit voltage gain of the tank circuit. All right. So we know this. VOC, our voltage is when open circuit voltage is evaluated, this is open, that value is just this one. And this value is given, and we know this value from the DC input, and this can be evaluated like this. So we have H infinity magnitude evaluate at the switching frequency is this one. Right? The second one is short circuit current. Short circuit current. We know this short circuit current that is given by ratio between this value, which is calculated here, and this value is the value we want to know. Then from here, this is determined like this, 1K something, right? So you have all the parameters known. So this value is known, this value is known, this is known, this is known. Then it's extremely simple to analyze this circuit. The simplest possible AC circuit, right? So let's take a look at the maximum power transfer condition. Previous lecture, we know this. This R match is the R. Delivers the maximum available power from the tank circuit. That is the magnitude of output impedance evaluated with input board shorted, which is this one. Okay, so this value is already known, which is R match. Then R match is this one. This value is known. Okay, so if R is selected like this, then this voltage is this one, which is VOC divided by square root 2, and this current is this one, ISC divided by square root 2. We proved this in the previous lecture, right? So the shape of ellipse, inverter ellipse is shown here. It starts from this ISC and ends at this VOC, not OS. I don't know why I'm doing this all the time. Okay, and it starts from here with very small r. When r is increased like this, okay, this is the r, given r. The operating point is here. If you further increase this from this to this value, this is a condition for the maximum power transfer, and the maximum power is given by this. This is the RMS value, okay. This is the this is the peak value. Okay, this is peak value. Then this is RMS value. Then this is what average power. Okay, so if you plot the power delivered through this resonant tank, the maximum value across here at this point, maybe it starts from 0 and goes to maximum value and return to this 0 like this, right? And the maximum power P max is given by this, which is product of this value and this value in RMS scale, right? So that is that. Okay. But this is the inverter ellipse at this particular switching frequency. If you change this switching frequency, everything will change. If you modify the input voltage, everything will be modified. But this is very essential to know this ellipse at this steady state operation, right? So there will be some variation from this, but you should know the reference curve. At least you should know the reference curve, all the voltages and current associated with that reference curve. Okay? So next one is tank design. So this is LCC tank. So LCC tank has L, series capacitor CS, and the parallel capacitor CP, and impedance of this series branch is JXS. S means series, which is this is a parallel branch, JXP, P means parallel, right? We know this, right? So this is the magnitude of voltage transfer gain at R is infinity. So this is open. Then the ratio between here to there is just the ratio of these impedances. So this XP divided by XS plus XP should be this number, equation number 1. Right? Equation number 2 is this. This is the shorted. This is the short circuit output impedance. So this is the shorted. Okay. Then output impedance is this JXS in parallel with JXP, which is this. Right? So magnitude of this is this. We have two equations for two unknowns. Obviously, this is the solution. So this XS is given, XP is given. If XP is given, CP is directly determined. There is only one circuit component, but here we have L and CS, and this XS is a series combination of this. So we have one additional condition to determine this 3 circuit component from 2 equations. Okay, so this is a procedure of selecting this capacitance and the inductor. Okay, first XP is this one, and the value in the previous lecture slide, you have this value, and this omega S is this 100 kilohertz. Then CP is given by this. Right? You have this equation, but we need to determine this L and CS simultaneously. That is a problem. So maybe we select the ratio of CS and the CP, factor 3. I explained the reason for this selection in the next slide. That is related with the line node efficiency. Okay? Somehow the ratio, you can select this one, maybe 3, 5, something like that. There is some criterion to determine this ratio. Somehow I selected number 3. So CS is 3 times CP. Okay, so CS is large. CS is large. Always CS is large. Then I have this one. So we determined this, and from this L is determined like this. So we selected all the 3 components, tank circuit component, CP, CS, and this is L, right? L, not CP. L, okay? All right, and I explain why we select this, why this spacing number. Okay, that requires some analysis. This is the curve of input impedance. You know how the input impedance of this LCC tank look like. Okay, this is the one. All right, this is the input impedance with output shorted. So we have this resonance. The resonance frequency is this one. When this becomes infinity, this is open, then resonance frequency is combination of this one and this series connection of these 2 capacitors. Okay, this value is smaller than smaller one. Okay, this is a parallel combination, not a series combination. Okay, then there is a 3 asymptote at high frequencies with this one. When this is shorted, high frequency asymptote is this one, SL. Right? So at these high frequencies, all the impedances merges with this asymptote. At low frequencies, we have 2 asymptotes. One is this one, SCS. Okay? 1 divided by SCS, and another one is 1 divided by SCS. This parallel combination. It's actually series combination. All right? But and evaluate the capacitance of this composite capacitance, we use the formula of parallel combination of resistor. So that is the reason why they are using this. So this becomes smaller, and which is this. Right? So if the ratio of this is very large, ratio of CS and CP is very large, then this one slope start here, another one start here. Right? Problem with that is all the input impedance curve merges together at this point. Okay, then they merge this single line, high frequency asymptote at very high frequencies, but in between there is this distance. Problem with this wide distance is related with the line node efficiency. Okay. Okay. First, above this region is what? ZVS region. Okay. So above this line is for ZVS operation. Let me use different color. This is ZVS region. And below this is what? All the impedance curve has this capacitive slope. So this is GCS. assume you are using the MOSFET switch, so you should be in GBS region. Okay, so this region, but in this region, this is what? This is a small resistance because this is the GIO curve. For the small resistance, you have GBS. For large resistance, which is this, you have GCS, right? So in between, from this F naught to F infinity, you have GBS for small r, GCS for large r, right? So maybe at this point, switching frequency is somewhere here. Then this is very small, this GIO. It is somewhere here. Then slope looks like this. Then we have GBS, desired operational region, right? And this determines, this is the borderline for good line node efficiency, this side, and poor line node efficiency, this side. The reason for that is, if we increase this load resistance from 0 to infinity, this load current is decreasing, right? Then this GI is decreasing, increasing, then tank current is decreasing. That is the good, right? The other way around is bad. In this region, you increased R, so load current is decreasing, but somehow this input impedance is decreasing, then tank current is increasing, right? So that is very bad, okay? Some case with open circuit condition, you are not delivering any power to load. The same tank current is just circulating through the tank circuit and just consumes the conductive loss. That is the very bad case, right? To avoid that case, if you have wide separation here, the switching frequency is somewhere here. Then if you increase this R, then this input resistance is decreasing this much. So you don't want to have the large gap like this. That hurts your line node efficiency. To avoid that situation, you have very narrow distance in between. That means the gap between this, right, GIO and the GI infinity will be wide. If you select this number very large, that is very bad because you have this much of the room to decrease your line node efficiency, which is bad. Okay, so to reduce this gap, you should limit this ratio less than 5. Okay, maybe 3 will be the good number. 10 is bad number, stupid number. 3 is maybe reasonable choice. Okay, with this choice, still this circuit has the problem because you select this structure, LCC structure, which is bad for this MOSFET switch. So we select this. So design is done. So we finished design. All design has been done. So we need validate this design. So this is the final value. This L, 1.96 millihenry, and 3.2 nanofarad, and 1.6 nanofarad, maybe reasonable number, right? And this reactance of this series, past series branch is this one at 100K, and this is the reactance of this parallel, okay? So first evaluate this R critical, okay? So R critical should be larger than 900 ohm. 900 ohm is what? This is actual load, and R critical is borderline between GCS and the GBS, and we want to have the GBS operation for this structure in between, okay? This GBS is available when smaller. If R, 900 ohm, is smaller than this value at this frequency, GBS is guaranteed. Otherwise, you are in GCS region, all right? So this is very important to check this out. So we need to evaluate this. This is equation for this R critical. We know this value. This is known from the beginning. Then we should know this one. So GI infinity is this one. GI infinity is this plus this. which is this. Magnitude of this is 765, and the GIO is shorted. Then impedance is just this series branch, which is this number, magnitude. Then R critical is this number. Okay, 1.47K. All right. So GCS operation at this frequency when this R is smaller than R critical. Okay. So this value is this number, and R is what? It was 900. So 900 is obviously smaller than 1000 something. So you are in GCS region. So this is good. Okay. This met the design specification, and converter is in GCS region. Right? If this condition is not met, then you need to deselect this ratio. Right? Somehow you are adjusting the ratio of CSCP. This number can be changed. This R critical can be changed. Then you still have this inequality to meet the requirement for the GCS operation. Right? If the GBS is not met, GBS condition is not met, then select the ratio differently to have this condition. So now we know this converter is designed as desired, and the GBS operation is guaranteed. So this shows the inverter ellipse at 100 kHz switching frequency with input voltage of 160. Any of this condition is changed, this will be changed, but this is the reference design. So, right, so this is inverter ellipse, okay? So operating point is any point on this line. For this R, rated R, 900 ohm, you have operating point here, and this R voltage is this one. This is the peak value, and RMS value is some, you just divide by this square root 2, okay? This is the RMS value of, no, this is the peak value, okay? I'm sorry, peak value, right? And maximum power is this one. So this converter can deliver 27 watt, but it is rated at 25 volt, 25 watt. So maybe this is a good design, okay? You don't have to unnecessarily increase this one. That will burden your tank design, okay? So this is the good design, and R match is here. This is the maximum power point. So maximum power is this times this in RMS version, and this is R critical, okay? So this structure, LCC structure in the middle range between F0 to F infinity, the R smaller than this R critical is the requirement for the GBS. So this region is for GBS. So R is somewhere here. For R match is here. So GBS is guaranteed. This value, and any value in between, RMS is guaranteed. If R cross this line, then the GBS operation will be broken, and your converter will be halted or destroyed. Okay? This is the implication of this inverter ellipse curve. So this is very important for the analysis, prediction of your converter operation, and to design this tank circuit. Otherwise, there are infinitely many choices, possible choices, but you should have some guideline to select properly. This is one example. Maybe this is the standard example in his book, Alex's book. Okay? I don't know, maybe other people is doing what. Okay, maybe they have their own guideline and they follow their guideline. So this is the guideline I choose to teach in my class. So this is proposed by Erickson. Most of the work is from Erickson, this part. Okay? So you have the reference chapter, right? Did that. The same information is here, but I transferred into easier explanation. Same thing, basically same thing. Okay, and performance evaluation. This is the input impedance curve. simulation result. I used at that time. Oh, this is the latest one. I don't know. 2008. Okay, 5 years ago. No, more than that. Okay, I used the PSpice. This is a PSpice. Okay, I just typed the simple LCC circuit and one resistor. I changed the resistor. Okay, this is the input impedance of R equals 0. This is 900. This was a mistake. This should be 900 because our value, design value is 900 ohm. Okay, so this is the input impedance for R, match the load, and input impedance of very large value, maybe 1 mega ohm, something like that. So it looks like this. Okay, this is GIO, and this is resonant frequency determined by this resonance between this L and the C. This is 0. It's shorted. So this is the L, CS, CP. So this is resonance curve between this L and CS, and this is the input impedance with this R becomes infinity, open circuit. Then you have another resonance frequency here. This F infinity as this one is this number and this number. So in between you have this, the merging point, crossover point, and equation for that as this one. You prove this. You follow the same approach we have taken for the LLC case. Then you will come up with this. This frequency is this one. This one. This is very close to our switching frequency. So this means switching frequency is somehow located in the vicinity, in the neighborhood of this FM. So at this frequency, input impedance of this converter, this tank circuit, remains almost constant. Because of the nature of this, around this A region, so GI is almost constant, regardless of the value of the R, load resistor. This is bad. This is relatively bad, very bad, because it hurt the line node efficiency, right? Because this IT remains the same regardless of value of this R, okay? When R is 0, we have impedance of this. R is infinity, we have impedance of this. Then tank current is the same, all right? So without delivering any power to the load, there is a tank current circulating. The amount of tank current is exactly same as the full load condition, which is very bad. Right? This shows the problem of LCC structure. Maybe you select the switching frequency somewhere here, all right? That problem can be reduced, but still you have a similar problem. This is bad, okay? Bad structure for you. That is the explanation about this. At this frequency region, GI is almost constant, regardless of value of R, because this is the merging point, right? Last time we went through, we proved this. Why input impedance is behaving this way is from the ET. Through the ET, we proved this. So all the input impedance is passing through this very narrow pinhole and dispersing like this, so they merge together. Okay, so this is the problem. So we may select this region. Still, this low frequency, line node efficiency will be bad because of this direction of magnitude of input impedance change. So from this, we expect the efficiency of this converter will be bad at line node condition. Okay. And operational status condition. All right, so we are comparing everything here. This is the input impedance plot. So this part is poor line load efficiency. This part is good line load efficiency. And this is the GBS region. This is the GCS region. In this point, this R, if R is lower than R critical, this is the R. Okay? This is R. R is lower than this value, like this one. This should be 900. I don't know why I keep on using 800. That does not make any sense. Okay? So this region is what? GBS. So we are in GBS region. Okay? R critical and R match. This is the borderline between CCM and the DCM operation. And this is the R for the maximum power transport. They match, they merge together at this frequency, FM frequency. That is the definition. It comes from the definition of derivation of this R critical, right? So, and switching frequency is this one, somewhere here. Same thing, right? One is 101 and one is 100, so they're the same. So operating point is this FM frequency, and R is below this value, so you are in GBS region. If R is increased beyond this value, then GBS will be destroyed. Okay? So there should be the hard limit on the maximum value of the R for the safe operation. And gain curve, transfer gain or DC voltage gain. Okay? So just transfer function from here to there is the DC gain. We have some constant in front. Okay? Then just to forget about that. Okay? So this is what? This is inverter, right? Inverter. Then we don't. I don't know, maybe some scaling factor is coming, this one, okay, but I think I didn't include that here somehow. I made a mistake, okay. Then transfer function from here, there is this one, okay. So this one is very easy to analyze if you use the asymptotic approach. Asymptotic approach means if you use one curve with for the very large R, okay. Assume this R is approaching infinity, then this value will be very large, this value will be large, then the parallel combination of reactance of this and resistance of this guy disappears, this guy disappears, so you have this one, okay? So you have this transfer function, which is this, right? So you have low frequency gain, and this is the pole, double pole, okay? This is low pass filter of Q of infinity. When this R is infinity, Q is infinity, R is very large, then Q is very large, smaller than infinity. So we have this low frequency asymptote here, and double pole is coming here. This is wrong, okay? This should be this resonant frequency, and this Q value is very high. So you have very high Q peaking here. So you are using this kind of characteristics because always we want to have high Q resonant tank, right? So this curve is valid when R is very large, okay? When R is very small, then you have this. R is very small, then this guy is gone. Then we only have R. Then this is LCSR, all right? This is this one. So this is standard form. This is the standard equation for the bandpass filter. Okay. This center frequency gain is when this L and the CS resonate, then this voltage and this voltage should be the same because impedance of this thing, they cancel as a 0. Then this voltage should be obviously same as this one. So at this center frequencies, the transfer function gain or DC gain is just 1. So we combine them together, okay? Graphically combine them together. Then we have this picture, right? So this is picture. Oh, okay, I forgot to mention this. At low frequencies, we have just voltage division. At low frequency, this is shorted. You have two capacitor. So this is the division factor is this. The low frequency gain, maybe CP is large. No, CS is very large. Then CP, there will be the 0 dB line. It goes up like this. So if you merge them together, you have this kind of characteristics. Okay, so this is the general feature of this voltage gain curve. When R is very small, you have this. R is increased, further increased, further increased, further increased, then you have this. All right? So small r, you have this. Then if you increase r, then it moves this. Resonant frequency is changing, and the peaking is increasing. This one. Okay? So it's not easy to see this from the original expression, but if you divide them into two regions, very small r, very large r, then this is obvious to see. Okay? So simulation result is shown in the next page. This is the P-SPI simulation, just simulation of this transfer function from here to there. Right? Then with very small r, relatively small r, 200 this curve, 400, 900, and switching frequency of our converter was somewhere here. Somewhere here. Something is wrong. Okay. Then if you increase further for 10 kilo ohm, you have this. If you increase further, it goes like this. All right. So from this curve, the operational mode can be predicted. All right. If R is this, then this region is what? GBS. I said this slope means GBS, right? This declining slope means increasing slope in input impedance. Then this is the region of GBS operation, maybe this much. This decreasing slope was something, I don't know, something like this, right? So if the switching frequency is here, then R is here, R value is here, you are definitely in GBS, right? So now switching frequency is 100 kilohertz, and R is, should be increasing, right? Oh, this one is okay. It's decreasing, right? So at this frequency, we have this slightly decreasing slope, okay? That means we have phase delay of 5 degree or 10 degree, very small phase delay. Still, this is the GBS, right? So from this graph, we show that our converter is in GCS because it has this slope. The converter is in GBS operation, okay? So R matched is still, I don't know, maybe GCS, I don't know. Okay? So this provide the information about the GBS and the GCS borderline. You extract the same information from the GIS plot. Okay? Magnitude of that provide the same information, and this value is 0 dB because at the resonance between this and this, it becomes shorted. Then this voltage should be same as this one. So you have 0 dB line here. This value, low frequency value, is a ratio between this one plus this one. You have some ratio, voltage division ratio. Okay, there is this curve. All right. So this is resonant frequency between these two reactive components. This is resonant frequency between three reactive components. Right. So our previous asymptotic analysis are correct. Okay, based on this simulation. Later on, you don't go through that asymptotic analysis. Just directly plot this. Okay, you know why curve looks like this. You know how to make use of it, right? How to use this information to justify your design and to predict performance of your converter. This is the expanded view of that. Okay, same the voltage gain curve. So target frequency, our target, design target was this magnitude of our voltage is this one, and input voltage, magnitude of input voltage is this one, fixed, okay, at this frequency. Then ratio between this one is this voltage gain curve. Then number should be 1.4, right? So just take a look at this. There are several curves. This one is for the 900 ohm, 100 kilohertz. This value is very close, slightly larger than 0 dB. Probably this magnitude is 1.04. The required value. Okay. Why this is happening? Why they match, exactly match? We designed all the circuit, tank circuit, to match this. This was our target, our aim. All right? So obviously we should have this. We followed all the procedure. The simulation results show that at this frequency, our voltage is exactly this one at the desired value, and when switching frequency as this one. Okay? And R is fixed. When R is varied or input voltage varied, then switching frequency should be changed to make output voltage constant. That for that purpose, we need to have the feedback controller, frequency control is required. Okay? Same as the problem of homework number 1. For the same reason, we should increase or decrease the switching frequency around this region. If this R is changing or input voltage is changing, to retain this value at the desired value, we should change the switching frequency with frequency control. Okay. All right, simulation result. This is the time domain simulation, open loop simulation, right? So very easy. Okay. The duty ratio of 0.5. You just modify this frequency. Okay. Then this is the reactive component. So we'll be watching this tank voltage and tank current and our voltage of current. All right. So for the steady state operational condition with, all right, let me finish up this section with this one. Okay. Oh, what happened? This file is corrupted somehow. This one too. Your handout is okay, right? All right. Somehow it has been corrupted. I don't know why. Okay. Just watch this. This is the VT, and this is the VT waveforms, IT waveforms, and our voltage and our current. Magnitude of this is the desired one. So our goal was 283, and this value is, this is not the, it's something else, right? This is our, it's not our design value. Design value is this, okay? You take a look at this. VT, IT, and IV, right? So this is the operational point. So operational point is here. This is for the maximum power transfer point, and everything matches. This is the prediction of IT, and magnitude of this one is 0.26. This value is very close to the 0.26. This is different from the sinusoidal waveforms, but peak value, somehow they match very closely, right? Same is true for this, our voltage and this load current, load voltage. This value is very similar to the design target, or your prediction, okay? And you take a look at these waveforms. This is tank voltage waveforms. Here, and zero voltage line is here, okay? So during this period, D1 is conducting, this period Q1 is conducting, this period D2 is conducting, Q2 is conducting. All right? So this means what? This is a ZVS operation. It's guaranteed at this regular load. Also, GCS operation is achieved with this R match. All right? So product of this one is what? This is the maximum power. Multiply them together and divide by 2, okay, to have the RMS version. That is the maximum power this tank can deliver, which is 28 watts something, all right? So that justifies our design. And finally, somehow I'd like to see the value for the open circuit current and the short circuit current. Based on our analysis, they should be the same, right? The current, tank current, should remain the same regardless of the value of R. R of 900, R of 0, R of infinity, they provide about the same tank current that produce bad, low line load efficiency. That problem comes from the structure of this tank circuit, okay? Not from the tank design. Tank is designed almost optimally, regardless of that problem. So you cannot escape that problem because of the structure limitation. That is the simple calculation of that. So GI infinity is this one, magnitude of that is this, and GI 0 is just series reactance, which is this, and GI at R of 900, you have this number based on this analysis, complex number analysis, magnitude becomes this one, they are the same, right? So this IT at low load and shorted load and standard load that is about the same, which is very bad, okay? Not desired, but cannot escape from this. This shows the simulation. What happened here? Okay, the simulation part is just the screw up. Okay, so you have the right handout. You can easily figure this out. All right. So that concludes the design of LCC, resonant tank. And tomorrow we will be discussing design of LLC, resonant tank inverter. Right? Okay? So becoming easy, right? It will be easier next time. And much easier next time. Right? Okay, thank you.